Okay, good morning. So, the last several classes, we have been discussing simplified neuron models, right? And today we'll start discussing what is called rate-coded neuron models. So, these are rate-coded neuron models as opposed to another class of models called spiking neuron models. So, let me kind of outline this. So, we began with Hodgkin-Huxley model, right, where you actually model the voltage action potentials. Then we discussed simple neuron models. Okay, here we discussed FN, ML, and INAPK model. And all these have certain common features. They are two variable models. Okay, and the second null, so two null lines. One is an N-shaped null line, other is either a straight line or like a Z shape, right, like a sigmoidal shaped null line. And here you get limit cycle right type activity. Okay, so you can model the voltage oscillations, etc. Then we began. So this is one, this is two. Then we began discussing what we call Izikevich models. These are also two variable models, but you can actually produce a action potential. Right, the rise is smooth, fall is sharp, and so on and so forth. So this is also two variable. Then we came down to leaky, integrate, and fire neuron model. Here, the voltage variation is like that, like exponential buildup, sharp fall, exponential buildup, sharp fall. Okay, now the actual action potential here, this is not an action potential because it's a very smooth waveform. So action potential is considered to be like a notional thing, where whenever this resetting of the voltage occurs, you just imagine that an action potential is generated like that. Okay, so these you think of them as a delta train, and this is a series of spikes, right? So these last two models are particularly, so the first are models of action potentials. The last two models are really examples of spiking neuron models, right? Okay, Hodgkin-Huxley model also produces spikes, but it's a more complicated model. These are like, this is a one variable model. These are more better described as spike neuron models. Now there is a different kind of model, which is not a spike neuron model, and that is called a rate-coded model. Because if you ask the question, what is the information present in the neuron's output? Right. So there are two schools of thought. One is the spike code, okay, which says that the information is present in the actual spike times. So you have to explicitly model the spikes and find out when they occur. Is the times, TI, right? That's most important. That is the idea. The other thing is called rate code, right? Where people believe that you don't have to actually, model the time of occurrence of the spikes, but it is enough. So if I have actual spikes which look like this, okay, which means here the spike frequency is small, here the spike frequency is large. So you can model this just in terms of spike frequency or spike rate like this. Okay, so modeling just the spike rate is called the rate code, right? So this is based on the idea that information present only in the rate, and you don't have to worry about the single spike times. So, and this is obviously much a simpler approach, right? So there are neuron models which are based on simply the rate code. So in case of rate code, the output of the neuron, right? There's some input and output. Output of the neuron will simply be a variable which goes between two limits, something like that. And depending upon the input, it doesn't oscillate or anything on its own. Usually they just follow the input and just goes up and down between two limits. The limits can be either 0 to 1, right, or minus 1 to 1, sorry, minus 1 to plus 1, etc. Now let us look at a couple of models based on rate code, and then in the next half of the talk, I'll talk about a different approach, right, which is based on oscillations. Okay, so we'll discuss something called binary neuron models. These are dynamic neuron models, which are based on the rate code. So their output simply varies between two limits. Okay, and a simple example of binary neuron model is given by the dynamics is given by these equations. Tau u dot is equal to minus u plus v plus I, and v is given as this function, this variable v is given as tan h of lambda, which is again dependent on lambda u. So you can think of it as a neuron model where the input is the current I, external current I. So this is like a function of time. Then output is v, okay, and you think of as an internal variable. So I influences the internal variable u, and u in turn influences the output v of the neuron. So this is given by differential equation, and this is quite a, it looks very simple but has very interesting dynamics. And let us see how to analyze this and what kind of dynamics you get. So the equation is tau u dot is equal to minus u plus v is basically tan h of lambda u plus I. So this is equal to v. Now, how do you solve this? Again, if you do something like a null line, we need to find out the fixed point. That is, when does the whole thing right become zero, right? And how does it vary depending upon I? This is what we need to find out. So for that, we'll do it geometrically or graphically like this. So the null line, there's not a, there's only one equation. So that equation is given as u is equal to tan h of lambda u plus I. Now, how do you solve this? Think of it as two different graphs. The advantage of phase plane, because we've been used to analyzing the phase plane, the systems in phase plane. So there we have two equations typically. X dot is equal to something, y dot equal to something. So you have two null lines, x null line, y null line. You plot both and then look at the intersection points and you get the fixed points. So here also, let's try to, even though there is a single variable here, let us try to take a similar approach by making this substitution. Let us consider two equations, y equal to u and y equal to tan h lambda u plus I. So solving this equation is nothing but, right, solving the intersection points of these two graphs, right? So let us look at how these two graphs look. So y equal to u is obviously a straight line. So here the x-axis is u and y-axis is y. So this is y equal to u. The other equation is tan h lambda u plus I. So here again you have two cases. So this is just to show that even such a simple equation has rich properties and quite non-trivial. So this is u, this is, you have two cases. One is let lambda be less than 1. If lambda is less than 1, the tan h, so lambda determines the slope of tan h function. Okay, so lambda is basically slope of tan h function at the origin. So if lambda is less than 1, the slope of this curve, this line is 1. Therefore, if lambda is less than 1, tan h will look something like this. Okay, so this limit is plus 1, this limit is minus 1. So it goes like this. The two curves intersect at origin. Okay, so origin is the only fixed point, and you can easily analyze and show that this is, so just look at second derivative and it will be negative, and you can see that second derivative of this expression, this whole expression. You can see that at origin this is stable. Okay. So in this curve, I'm assuming that I equal to 0, right? And so this only origin is stable for lambda less than 1. So nothing very interesting happens. But if lambda is greater than 1, also assume that lambda is much greater than 1. So then what happens is this tan h function will show a sharp slope at the origin. And okay, it has two saturating, two wings where it saturates, -1 and +1. And now it has three fixed points. Okay, this is similar to the 3 fixed point case that we saw in the Fujin-Ogumo model, right? And there also we found that the 2 points on the flanks are stable. So you can here also you can show it's a stable point. This is also stable. When you can analyze it and look at second derivative of this expression and find out. And this is unstable. It's not a saddle because saddle needs 2 variables. There's only a single variable. So this is unstable. So what that means is if the system starts here, it will stay there. If it starts here, so if we start from anywhere on the positive side, for U positive, it will kind of land here, get attracted here and land here. If it starts anywhere on the negative side, negative U, it will land here. But if you keep it at origin, it will stay there. Okay, but on a small perturbation, depending upon which side you are perturbing, it will go towards +1. This is close to +1. It will go to either this point or this point. So the system has the property of bistability, right? Once you push it, you may imagine it is like in a ball in a what is called a bistable well. Suppose you have a well shaped like this, right? And you leave a ball here, it will roll down to this point and stay there. If you leave it here, it will roll down here and stay there, right? If you leave it in the middle, if you leave it exactly on this hill, it will stay there. But if you topple it slightly to one side, it will roll over here or here. Okay. So you can actually construct an explicit potential even for this system, but it's okay. So now what happens is if you vary, this is for I equal to 0, right? Now if you vary I, then if let me make some space here. So if vary I, let us say I is much greater than 0, okay, has a high positive value, or then epsilon plus, which is greater than 0. So then what happens is, so if I is a positive value, then you can see that in this function, if I is positive, this whole curve is lifted up, okay, and this thing remains the same. So this remains the same, and the other tangent is lifted up. Imagine the whole tangent is lifted like this. It will go something like this. So when that happens, you can see that there's only one fixed point, and that is positive. Okay, this is also stable. You can show that it's stable. So similarly, when I is much less than some epsilon minus, which is less than 0, then the opposite thing happens. So this curve is this line is the same, but so this tangent will completely go down. Right? You have only one fixed point. You have only one fixed point. Oh, and that is negative, and it's stable. So basically, what happens is, as you vary I from minus infinity to plus infinity, at certain critical value on the negative side, you have only until then you have only one fixed point, right? And beyond that, you will have bistability. It will have 2 fixed points, and beyond that, again, you have one fixed point. So that can be seen like this. So as input current is varied, up to one point, it has only one fixed point, which is a negative value, close to -1. So when you take it to the positive side, up to one point, it has only one fixed point, which is positive. And between that, it has bistability, right? And also when you go from plus to minus, the positive fixed point remains stable for some time until the state rolls over to the negative side and becomes negative. And similarly, when you go from negative to positive, the negative fixed point remains stable for some time before it switches over to the positive side. And point where the transition occurs at different points when you're going from positive to negative and opposed to negative to positive. So you see a kind of hysteresis behavior. Okay, you go like this, and you go from positive, and you come back from negative, right? You go like this, go in a different way. Okay. So you can, you might have heard that if you look at magnetic materials, which are materials which are used for modeling memory, for implementing memory in computers, they also have 2 states because a magnetic, because memory in a hard disk is based on the spin of a magnetic particle. right? And it can be it can have a positive spin or a negative spin. And when you vary the magnetic field from say positive to negative, that spin varies at some critical value from positive to negative. And there also you see the same kind of hysteresis. And interestingly, this kind of neuron model can also be used as a memory, as a memory unit, because it has the property of biastability, and once it stays in a given state, it won't change until you perturb the input drastically. So in a small perturbation, it will still remain close to that positive value. Okay, so that's a very simple red-coded model, because here the output V it doesn't show any spikes, right? V is not like this. V shows a continuous variation depending upon the input. So it is a rate code. So people have then made up something even simpler. They've got rid of the dynamics completely, because in the previous model, which is a binary model and a red-coded model, right, the output still has dynamics in the sense it has a memory. It depends on past history. So if you are going from high positive to negative, it will show one behavior, negative to positive to show one behavior. That means it depends on history, because it's determined by a differential equation. But whereas here the static neuron model, right, simply there is no dynamics in it. There is no differential equation. This is probably the simplest kind of neuron model. So where a neuron receives inputs from many other neurons, okay, and produce an output Y, and these are the inputs coming from other neurons, X1, X2, Xi, Xn. And here we also, since it's a very simple model, we can also do something more than what we have done in the previous case, all the previous neuron models. Because in the previous neuron models, we only model the input-output behavior. If I give an input current, what is the output? Right? We call it V, call it Y, whatever. What is output? We didn't model the synapses in some of these single neuron models. But whereas in this static neuron model, so you can model synapses also. So these are the inputs. And inputs, imagine, are going over synapses. This is W1, Wi, Wn. So Y is equal to a function f of all this sum of all these inputs, sigma Wi xi, and you also assume there is some kind of a bias term theta, because neurons typically have a threshold value, right? They fire only when the input crosses the threshold. So here the input is the net effect of all these inputs coming from other neurons passed over the synapses which have certain weightage. And since you have excitatory synapses and inhibitory synapses, these weightage values can have positive or negative values. So sum all of these up, right, and see if it passes a threshold. If it passes a threshold, output Y is thought to be 1, otherwise it is 0. Okay, which means this f function is like a step function, which is what you see. So this is a unit step function, and f of x. So this is the simplest kind of neuron model. It's also called McCullough and Pitt's neuron model, after the people who developed it. So, and this happens also to be one of the first neuron models in artificial neural networks. So, because now we are coming to artificial neural networks. Because we began with more biologically inspired neuron models like Hodgson, very biologically inspired. And then we looked at even more biologically detailed neuron models. Right, we looked at dendritic processing and table equation, all that stuff. We progressively simplified it. Now we came to a point, it is reached a point of almost absurdity. You cannot simplify it any further. We can't call it neuron anymore. So even this kind of a model, although it's very powerful, you can do a lot of interesting things. If you put this in a network structure, if you talk to a hardcore biologist, they may not take it as a serious neuron model. Okay, so it's really very simple. But this is a kind of neuron model that is used in artificial neural networks, and also mostly in the modern deep learning literature. This is a kind of neuron model that people use. So here again, you can use several variations of this model. There is so this nonlinearity that we use, f, can go from 0 to 1. So that's when you use a step function, or it can go from -1 to 1 like this, right? So that is when you use the signum function, right, or just SGN, right, which is a negative, which is -1 for negative and +1 for positive. Okay, and the discontinuity at the origin. So these two are called hard limiting nonlinearities because there is a discontinuity. The nonlinearity is hard limiting. It abruptly changes from the lower value to the higher value. Then there are smoother versions of this because the disadvantage of this kind of a model mathematically is there's no derivative doesn't exist at origin. So your calculations become problematic. Then therefore people have modeled a simpler version of this, a smoother version of this. So in the 0 to 1 convention, right, instead of step function, so this is a hard limiting version. So this is a step. The smoother version of this is what is called as logistic function, okay, which looks like this, which goes from 0 to 1, but asymptotically. So at the origin, this is 0.5. Okay, and this is given by the function y equal to 1 by 1 plus e power minus lambda x. And lambda is the slope of this sigmoid function at the origin. And typically lambda you take to be a large positive number. So similarly, if you look at the -1 to 1 convention, there also there is a smoother and differentiable version of the signum function, that is a tangent function, okay, which goes from -1 to +1 at infinities. Okay, so that completes the discussion of our single neuron models, right? Especially the single, especially the two categories, the rate coded and the spike neuron models. So now I want to present a third kind of neuron model, which is not generally recognized as a standard neuron model, but there is a kind of a lot of many groups all over the world who are saying that the basic unit of computation in the brain cannot be like a single neuron, but a group of neurons. Okay, what is called a neural ensemble, right? And therefore, if that is the case, if we assume that, if we accept that, so then the model itself will be quite different, look quite different. So you can call that an oscillator neuron model. So let us, and our lab is like a strong proponent of this approach. And let me say a little bit about that.